Now let's look at proximity sensors. A proximity sensor simply tells the controller whether a moving part is at a certain place. A limit switch is an example of a proximity sensor. A limit switch is a mechanical push-button switch that is mounted in such a way that it is actuated when a mechanical part or lever arm gets to the end of its intended travel. For example, in an automatic garage door opener, all the controller needs to know is if the door is all the way open or all the way closed. Limit switches can detect these two conditions. Switches are fine for many applications, but they have at least two drawbacks. Being a mechanical device, they eventually wear out, and they require a certain amount of physical force to actuate. Two other types of proximity sensors, which use either optics or magnetics to determine if an object is near, do not have these problems. The price we pay for these improved characteristics is that they require some support electronics. Proximity refers to a transducer that can determine if something is in the proximity of the switch. Although technically also proximity switches, limit switches are colloquially called limit switches as opposed to optical and magnetic proximity switches that are called proximity switches or proxies. Optical proximity sensors, sometimes called interrupters, use a light source and a photosensor that are mounted in such a way that the object to be detected cuts the light path. In Figure A, a photodetector counts the number of cans on an assembly line. Optical proximity sensors frequently use a reflector on one side, which allows the detector light and source to be housed in the same enclosure. Also, the light source may be modulated to give the beam a unique signature, so that the detector can distinguish between the beam and stray light. Four types of photodetectors are in general use: photoresistors, photodiodes, phototransistors, and photovoltaic cells. A photoresistor, which is made out of a material such as cadmium sulfide, has the property that its resistance decreases when the light level increases. It is inexpensive and quite sensitive, that is, the resistance can change by a factor of 100 or more when exposed to light and dark. Figure A shows the typical interface circuit. As the light increases, RBD decreases, and so Vout increases. A photodiode is a light-sensitive diode. A little window allows light to fall directly on the PN junction, where it has the effect of increasing the reverse leakage current. Figure B shows the photodiode with its interface circuit. Notice that the photodiode is reverse biased and that the small reverse leakage current is converted into an amplified voltage by the op-amp. A phototransistor in Figure C has no base lead. Instead, the light effectively creates a base current by generating electron-hole pairs in the CB junction. The more light, the more transistor turns on. The photovoltaic cell is different from the photosensors discussed so far because it actually creates electrical power from light. The more light, the higher the voltage. A solar cell is a photovoltaic cell. When used as a sensor, the small voltage output must usually be amplified, as shown in Figure D. Optical sensors enjoy the advantage that neither the light source, the object to be detected, nor the detector have to be near each other. An example of this is a burglar alarm system. The light source is on one side of the room, the burglar is in the middle, and the detector is on the other side of the room. This property can be important in a case where there is no convenient mounting surface next to the part to be measured. On the other hand, keeping the lenses clean may be a problem in some industrial situations. In 1879, E.H. Hall first noticed the effect that bears his name. He discovered a special property of copper and later of semiconductors. They produce a voltage in the presence of magnetic field. This is especially true for germanium and indium. The Hall effect is the production of a voltage difference, the Hall voltage, across an electrical conductor transverse to an electric current in the conductor and to an applied magnetic field perpendicular to the current. That's quite a mouthful. The Hall effect, as it is called, was originally used for wattmeters and Gauss meters. Now it is used extensively for proximity sensors. The picture shows some typical applications. In all cases, the Hall effect sensor outputs a voltage when the magnetic field in which it finds itself increases. This is done either by moving a magnet or by changing the magnetic field path. But the value of the Hall voltage does not depend on the field moving, only on the field being there. The diagram shows how the Hall effect works. First, an external voltage source is used to establish current I in the semiconductor crystal. The output voltage VH is sensed across the side of the crystal perpendicular to the current direction. When a magnetic field is brought near, the negative charges are deflected to one side, producing a voltage. The relationship can be described in the following equation. VH is equal to KIB over D, where VH is the Hall effect voltage, K is a constant depending on the material, I is the current from the external source, B is the magnetic flux density, and D the thickness constant. The Hall voltage equation states that VH is directly proportional to I and B, that's the current and the magnetic flux. If I is held constant, then VH is directly proportional to the magnetic flux density. Therefore, the output is not really on-off, but over a short distance, somewhat linear. To get a switching action, the output must go through a threshold detector, like that illustrated in Figure A. This circuit uses two comparator amps to establish the high and low switching voltages. When VH goes above 0.5 volts, the top amp sets the RS flip-flop. When VH goes below 0.25 volts, the bottom amp resets the flip-flop. For this circuit to work, we need to make sure that the magnet comes near enough to the sensor to make VH go above 0.5 volts and far enough away for VH to drop below 0.025 volts. A complete Hall effect switch can be purchased in IC form. One example is the Allegro 3175, shown in Figure B. It includes the sensor X, the cross-current drive, and the threshold detector. The transistor turns on when the magnetic field goes above 100 Gauss and turns off when it goes below negative 100 Gauss. The transistor can sink 15 milliamps, which can drive a small relay directly, or a TTL digital circuit. Hall effect sensors are used in many applications, for example, computer keyboard switches and proximity switches in machines. They are also used as the sensors in toothed rotor tachometers discussed earlier in this chapter.